Fusion reactors, the energy source of the fusion future. Enormous as the energy produced by the fission is, the fusion of light nuclei to form heavier ones can give out even more per kilogram of starting materials. It seems possible that nuclear fusion could become the ultimate source of energy on the Earth, safe, reliable, relatively non polluting, and with the oceans themselves supplying limitless fuel. On the Earth, where any reacting mass must be very limited in size, an efficient fusion process cannot involve more than a single step. Two reactions that may eventually power fusion reactors involve combination of two deuterons to form a tritium and a proton, or their combination to form a helium-3 nucleus and a neutron. Both deuteron reactions have about equal probabilities. A major advantage of these reactions is that deuterium itself deuterium is present in seawater and is cheap to extract. Although its concentration in seawater is only 33 grams per meter cube, this adds up to about 10 to the power 15 tons of deuterium in the world's oceans. The deuterium in a gallon of seawater can yield as much energy through fusion as 600 gallons of gasoline through combustion. The first fusion reactors are likely to employ a deuterium-tritium mixture because the DT reaction has a higher yield than the others and occurs at lower temperatures. This gives 4 mega electron volts, this gives 3 mega electron volts, this gives 17 mega electron volt and occurs at lower temperatures. The seawater contains too little tritium to be extracted economically, but it can be produced by the neutron bombardment of two isotopes of natural lithium. So when we bombard lithium 6 on a neutron on a lithium 6, we get a tritium and helium, and when we bombard neutron on a lithium 7, we get tritium, helium, and a neutron. In fact, plans for future fusion reactors include lithium blankets that will make the tritium they need by absorbing neutrons liberated in the fusion reactions. At the required temperatures of fusion reactors, fuel will be in the form of a plasma, which is fully ionized gas. Break-even occurs when energy produced equals the energy input to the reacting plasma. Ignition, a more difficult and perhaps unnecessary target, occurs when energy is produced for the reaction to be self-sustaining. A successful fusion reactor has three basic conditions to meet. The plasma temperature must be high so that adequate number of ions have the speeds needed to come close together to react despite their mutual repulsion, taking into account that many ions have speeds well above the average and the tunneling through the potential barrier reduces the ion energy needed. The minimum temperature for igniting the DT plasma is about 100 million Kelvin, which corresponds to an ion temperature of kT of 10 kilo electron volt. The plasma density must be high to ensure that collisions between nuclei are frequent, and the plasma of reacting nuclei must remain together for a sufficiently long time. Tau, how long depends on the product, and tau, the confinement quality parameter. In the case of DT plasma with kT is equal to 10 kilo electron volt, and tau must be greater than roughly 10 to the power 20 second per meter cube for break even, more than that for ignition. Apart from stellar interiors, the combustion of temperature, density, and confinement time needed for fusion thus far has occurred only in the explosion of fission. Incorporating the ingredients of fusion reactor reactions in such a bomb leads to an even more destructive weapon, the hydrogen bomb. Confinement methods. The approach to the controlled release of fusion energy thus has thus far shown the promised use of a strong magnetic field to confine the relative plasma. In the Russian designed tokamak scheme, the magnetic field is a modified torus donut in form. In the Russian, tokamak stands for toroidal magnetic chamber. Because the field lines are is of a purely toroidal field are curved, an ion moving an ion moving in a helical path around the field lines will drift across the field and escape. To prevent this, a tokamak uses poloidal field whose field lines are circles around the toroidal axis. The poloidal field is produced by the set up in the plasma itself by the changing field of an electromagnetic magnet in the center of the toroid. The current also heats the plasma. Once the plasma is sufficiently hot, the current needs little help to continue. So conditions for break-even: energy output equals energy input, and ignition. Self-sustaining reaction of fusion reactor. Existing reactors have come close to a break-even. The projected International Thermonuclear Experimental Reactor is intended to go beyond it. The Joint European Torus is an experimental tokamak fusion reactor at Culham, England. The reactor has delivered 16 MW with a power unit of 25 MW, encouraging close to break-even. ITER, the planned International Thermonuclear Experimental Reactor, represents what is hoped to be the final step before practical fusion energy becomes a reality. ITER is currently sponsored by Japan and several European countries. The United States pulled out of the project because of concerns about its original design and cost, and Russia withdrew, except for providing some staff because it cannot afford to participate. The redesigned ITER is expected to generate some 400 megawatt from deuterium tritium reactions to weigh 32,000 ton, cost 3 billion, and take 10-15 years to build. Superconducting magnets, a large part of the cost, will keep the reacting ions in a donut-shaped region whose volume is that of a large house. About 80% of the energy released will be carried out off by the neutrons that are produced, and these neutrons will be absorbed by lithium pellets in tubes that surround the reaction chamber. Circulating water will carry away the resulting heat. This is the heat that will be used in a commercial reactor to power turbines connected to electric generators. Even if ITER works as planned, though not every pessimistic observer of the fusion program is likely to convert to the cost, fusion reactors will certainly be enormously complex and expensive and not wholly safe. Lithium is an extremely reactive metal that burns or explodes on contact with water. Also, when lithium absorbs neutrons in the reactions, the radioactive tritium is produced, hence, an accident could be catastrophic. Of course, the optimist could turn out to be correct, and fusion will become the preferred energy source of the future. But even if this happens, many decades lie ahead in which problems will remain. Fusion reactors employ an established technology, and ways exist to make them very safe. But memories of Three Mile Island and Chernobyl, plus continuing questions about the disposal of radioactive waste, continue to affect their public image. Meanwhile, fossil fuels are being used up, and burning them produces enough CO2 to affect weather and climate. Such green energy sources as such as solar cells and wind turbines are unlikely to provide more than a small, though welcome fraction of the energy needs. An energy strategy for the world that is both sensible and widely acceptable is not obvious. The world's most powerful laser, located in Lawrence National Laboratory in California, is used in inertial confinement experiment, and its output is 60 kJ per nanosecond. Pulse is divided into 10 beams that are directed in a tiny deuterium tritium pellets in, in an effort to induce fusion reactions in them. The most powerful tokamaks today have attained plasma temperatures of 30 kilo electron volt and confinement quality n tau values of 2 into 10 to the power 19 seconds per meter cube, but not break even. Break even will probably have to wait for a planned international thermonuclear experimental reactor. An entirely different procedure called inertial confinement uses energetic beams to both heat and compress tiny deuterium tritium pellets by blasting them all sides from all sides. The result is in effect a miniature hydrogen bomb explosion, and a succession of them could provide a steady stream of energy. If 10.1 megapellets are ignited every second, the average thermal output would be about 1 gigawatt and could yield 300 megawatt or so of electric power, enough for a city of 175,000 people. Laser beams have received the most attention for inertial confinement, but electron and proton beams have promise as well. The beam energy is absorbed in the outer layer of the fuel pellet, which blows off outward. Conservation of momentum leads an inward shock wave that must squeeze the rest of the pellet of about 10 to the power 4 times its original density to heat the fuel sufficiently to start fusion reactions. The required beam energy is well beyond the capacity of today's lasers, though perhaps not of future ones. Particle beams are closer to reaching the needed energy but are much harder to focus on tiny future pellets. Research continues, but magnetic confinement seems closer to the goal of a working fusion reactor. So that's all. See you in the next one.